So now we begin looking at general vector spaces. So far in the Euclidean vector spaces, of course, are limited to just R2, mostly R2 and R3. And we've looked at Rn, of course, no doubt, but when we call it Euclidean because the norm used there is in fact just the Euclidean norm. Now we want to look at general vector spaces, which the Euclidean vector spaces is a member of. In fact, it's one particular vector space or a set of spaces. General vector spaces, here we would like to extend the idea, for instance, of vector spaces to anything. For instance, polynomials, functions, derivatives. It could be anything, in fact, matrices. So we want to start looking at vector spaces as I mentioned in the introductory, perhaps, lectures, that the concept of vector spaces is a very large, encompassing concept. So we start by looking at the 10 axioms. So the vector space V is, as I said, a non-empty set of objects, and on these objects we can have only two operations: addition and multiplication by a scalar. So by addition we mean a rule of associating with each pair of objects U and V. Let's call them U and V that both belong to V. Of course, they're objects in V, capital. And we represent this addition as the standard addition symbol U plus V. It's called the sum. Okay, we call this the sum of U and V. Now, just bear with me. Some of the terms may some of these ideas. It might seem like a trivial idea, but just bear with me for a moment. So, by scalar multiplication, we mean a rule for associating with each scalar k. Okay, each object U in V, the object called ku, which is multiplication by the scalar, and which is the scalar multiple of U by k. Okay, that's what we call it. Now, if the following axioms are satisfied by all objects U, V, W in V and all scalars k and m, then we call V a vector space. Otherwise, it is not a vector space. So let's start looking at these axioms. So these axioms are a very key and important idea for the definition of a vector space. So let's see what these are. The first one and the most important of the axioms is the closure under addition. So it's closure under addition. Okay, so what closure under addition means is that U and V, as we have assumed, belong to V. So U and V belong to V, then the sum U plus V also belongs to V. So that's what it says. That if U and V are objects in V, then U plus V must be in V as well. So that's a very important axiom and something we haven't actually seen before. Some of the remaining properties now that I will go on the addition side are properties that are inherited from Euclidean and vector spaces, R1, R2, Rn, and so on. So these are, of course, for instance, the commutativity of addition. So U plus V is equal to V plus U. Another obvious one, and again inherited as well, is U plus V plus W equals U plus V plus W. Similarly, now the fourth one, although this is inherited, but something that we will need to work on quite heavily, and it is the source of a lot of confusion sometimes. There is an object 0. Now this is about the 0 object. Okay, the 0 object in V. Okay, every vector space has a 0 object V. It's called the 0 vector. Okay, the 0 vector. Now, its definition is that when we add this vector to any vector, okay, it gives us back what we started with, which is U. So in this case, when we add 0 to U, we get U back. Again, as I said, please bear with me. The ideas seem so simple, but these are bare-bone ideas that help us even to develop an entire algebra. They can. Okay, so let's move on. The next property then, and it actually is associated with the 0, is the definition of something called negative vector, okay, or minus u. So for each u in V, there is an object minus u, which is also in V, okay, and it is known as the negative of u, okay, it's called the negative of u, and it is such a vector that whenever we add the negative vector or the negative of u to u, we in fact end up with the zero vector as defined in 4. Okay, so those are the first 5 axioms, and all of these are really basically the closure axiom and then the addition axioms, and then we have, of course, the definition of zero vector, a very important definition, in fact. Okay, let's move on then. The 6th axiom, the 6th axiom is known as the closure under scalar multiplication. Closure, okay, under scalar multiplication. Okay, closure under scalar multiplication. Okay, this is another a slight shift now. So first, the first 5 relate to addition. Now we look at closure under scalar multiplication, and what it means is that if u of course being in V, then the element and then the object ku also is in V. Okay, so when we multiply it by any scalar, it remains within the vector space. Now some axioms related to scalar multiplication. Again, these are inherited. So that's a straightforward one, very obvious. So in the same way, if we were to add two scalars, k and m are both scalars here. Okay, so k and m are scalars. Okay, so k plus m times u, for instance, is ku plus mu. 9th axiom is if, in a similar way, we have multiplication, okay, then that is the same as km times u. The last one, by no means the least one, is multiplication by 1. When we multiply 1 by u, u by 1, we get u, in fact. So those are the 10 axioms that go to define a vector space. Now I'm going to look at some examples and demonstrate how something can be a vector space. And the best thing is to start with a familiar example, and that familiar example is, of course, that I want to use is, of course, and I'll keep the axioms here, and that is looking at, of course, the familiar Euclidean vector spaces. Okay, so the Euclidean vector space, the Rn vector space, which would cover all of them. So we look at Rn, for instance. So if V would be, in fact, Rn, then u plus V is the standard addition of vectors. So u plus V, as you know it, is u1 plus v1, comma u2 plus v2, etc. So I don't want to repeat everything, but anyway, where u and v are belonging to un. So I am assuming you understand that as we have done earlier. So they belong to Rn. And k times u would be, of course, ku1, ku2. So this simply defines the operation of what is the multiplication by the scalar. So this is standard in the Euclidean vector space. So closure under addition. How do we demonstrate closure under addition? What that means is, essentially, if you take two vectors in Rn and you add the two vectors according to this definition of addition, or the sum, what results? What actually results is a vector that is also in Rn, because when I add u and v, I'm not going to get an extra component. I'm still going to have n components. So n components means it still belongs to Rn. So clearly, this is closed under addition. U plus v is v plus u. These are all inherited. The zero vector is just all components 0. So the zero vector is in fact all zeros. as it is in Rn, as we have seen it before. Minus u is again using the definition of scalar multiplication as well. Keep that in mind. So minus u means the minus negative of all components, and when we add that to u, it's going to give us the zero vector. So it's closed under. So that is the fifth axiom is fine. Closure under scalar multiplication means when you multiply u by a scalar k, are you going to get n components? We are, of course. So therefore, the resulting vector when u is multiplied by k is still a vector that is in Rn. So we therefore have closure under scalar multiplication. And the remaining axioms are simply inherited in their obvious, as I said, don't really require proof. So I'm not going to prove them, essentially. They're all true, in fact. Now, that's our first example. Let's look at another example. Now I want to look at a very interesting little vector space here, something that you have not seen before. So now we're going to look at the space of 2 by 2 matrices. So V is going to be, V is the space of 2 by 2 matrices. Okay, so that's what we're going to start with. So the objects that we talked about in the vector space V are all matrices that are of size 2 by 2. So there's an infinity of them. So all 2 by 2 matrices basically are contained within the vector space V. Addition of the vectors is defined as standard addition in matrices. So for instance, here, as I am showing you, so here you can see when I add the sum of the two vectors, where each vector is a 2 by 2 matrix, as you can see, it is the standard addition of matrices, whether 2 by 2 or anything. Now scalar multiplication is of course k times u, so that's what we get when we multiply. That's standard multiplication of a matrix by a scalar. Everything in the matrix is multiplied by that. So now that defines, now let's go on to the zero vector. The zero vector is in fact the zero matrix, 0 2 by 2 matrix. Okay, and that should be sufficient. Now let's start looking at the axioms very quickly. Now just look at the first one. If u and v, if we take two vectors from V, that means two matrices that are 2 by 2 matrices, and we add them, what results? Well, what we get is another 2 by 2 matrix. So therefore we have clear closure under addition. U plus V is V plus U. Standard addition of matrices according to this definition of matrices clearly is fine. 2 and 3 are fine. 0 belongs to V, the zero vector. Clearly when we add this matrix as you see here, when I add this to any matrix, it is simply going to give me that matrix back. It adds nothing of value to any of the 2 by 2 matrices. The negative of the matrix again is again a very straightforward idea. So if I were to take u and add it to what is minus u, then let's just quickly look at that. It's going to be minus u11, minus u12, minus u21, and minus u22. So when I add that to u, I'm clearly going to get this here. So it's going to be the zero matrix. So that axiom 4 is satisfied. Axiom 5, sorry, is satisfied. Scalar multiplication. When I multiply, as you can see here, what is that? It's still a 2 by 2 matrix. So therefore, it is closed under scalar multiplication as well. And the remaining axioms are pretty straightforward. And the last one, again, is also a very obvious one, which is 1 times, where 1 is the scalar. So scalar multiplication is used, so it'll still give us u. So this is obviously, as all 10 axioms are satisfied, this is a valid bona fide vector space. Now I want to quickly show you one example where something is not in fact a vector space. So let's do that. Let me just give me 1 sec here. So here let R2, let V be R2 in fact. So it's an R2 space where of course we will define addition as standard. Okay, so it's u1 plus v1 comma u2 plus v2. Clearly u and v belong to R2 in this case. So, but here's what we're going to do. We're going to define scalar multiplication a little differently. that it's this. Now, under these definitions, let's see, do we have, do the axioms satisfy? Closure under addition, clearly we had two vectors. We're still going to get vectors in R2. So addition is not going to add a component. So therefore, it is still closed under addition. Now, axiom 2, axiom 3, no problems. Axiom 4, also no problem. The zero vector, not an issue. The negative vector also is not an issue. No issues, no problems there. The problem that we face here, interestingly, is when we look at the final axiom. The last axiom, which is 1 times u, means we get, according to the scalar multiplication, this is going to become u1, 0. The problem is that is not equal to u. So therefore, axiom 10, okay, is not satisfied. Axiom 10 fails. So it fails. Therefore, this is not a valid vector space. So that's this is a demonstration of something that that is not a vector space. Okay. Last one other example I want to look at, and this is from Anton, the book the reference text for this course that I recommend quite strongly, is another vector space that in fact is a space of positive real numbers. Okay, so positive real numbers means that you are looking at just u and v. So there's no underlying. So these are not multi-component. They're not matrices or anything. They're just numbers. And we define u plus v to be the product of uv. Okay, so just to be clear, v is positive real numbers. Okay, just positive real numbers, set of positive real numbers. Okay, so u plus v is uv. Okay, and ku would simply be ku like this, but interestingly, what we're going to do is we're going to define it as u to the power k. Now, this may look very odd, but that's the way it is. And this is how we're going to define it. And now we're going to check if something as strange as this can actually be a vector space. So let's start with the closure axiom. When we add the two, when we add any two numbers, in this case we take their product, what results? A number. So therefore, we have closure under addition. It is a real positive number. So if we take two positive numbers, the product of two positive numbers is also a positive number. So therefore, we don't have any problems there. So it is closed under addition. When we add u plus v is the same as vu because product is the same. U times v is the same as v times u. So it is closed under. So the second axiom is fine. Third axiom is fine. What about the zero vector? Well, first have to define it actually. This is very interesting. What is in fact zero in this case? Well, we have to go back to the definition. Zero is something when you add, so the zero is going to be, so the zero vector, we're going to have this situation. So it's going to be 0 plus u, any number, okay, is actually 0 multiplied by u. Now we know multiplication is standard. Now that's going to give me 0. So I have to be very careful. I have to think, what should I get back? What should I get back? What I want is u. The only way I can get u is I have to change this. So 0, the zero vector is in fact the number 1. Think about that. It looks very confusing, but it means that when I add the 0 to u, it's the same. The zero vector is in fact the number 1. Okay, so what I'm going to say is, sorry, I rewrote that. Pardon me. Let me write. So what I'm saying is that the zero vector, okay, this is what I want, by the way, but I don't get this. You see, this is going to be 0 now if I multiply by 0. So the zero vector is the number 1, in fact. Now, if you think about it, 1 plus u is 1 times u, and it's equal to u. So in other words, when I add the zero vector to any vector, I get that vector back. And that's what will happen for anything. So that's a definition of one that I have to be very clear about. A definition of 0 is, it is not 0 as the number 0 now, which again looks very confusing, but it is still consistent. Now let's move further. So minus u though is another very interesting one. So we have to look at this. Minus u is the same as the scalar minus the negative 1 multiplied by u. And according to the definition here, that's u to the minus 1, which is 1 over u. So that would be the definition of it, okay? But does it actually satisfy its complete definition, which is, that's how we calculate it, but does it satisfy its definition? Well, let's see. U plus minus u is in fact going to be u multiplied by 1 over u, which is equal to 1. And what is 1? It's the 0 vector. So in other words, the axiom is satisfied because the 0 of this vector space is the number 1. Okay. Very interesting. Let's move a little further, and we're almost there. The other axioms, a closure under scalar multiplication is not a problem because when we raise any number to another number, we still get a positive number. It's not going to affect the sign of the number, so we're still fine. So it is closed under, scalar multiplication. The remaining axioms are reasonably straightforward, but I will just demonstrate one of them. For instance, k times u plus v. If I look at that, that's going to give me, in fact, remember, u plus v, okay, is uv. So it's going to be k times, first of all, uv, which means it's going to become uv to the power k. Okay, because it's a scalar multiplication. So you need to work this out quite carefully. All right, now, what is that? Well, that's equal to u to the k into v to the k, right? But wait a second. U to the k is ku, okay? And it's multiplied by kv. But multiplication is in fact addition. So that's ku, okay, plus kv. Sorry. Alrighty. Very interesting as well. So that axiom is also satisfied. And similarly, the last axiom is 1 times u, which is u to the power 1. So 1 times u is u to the power 1, which is equal to u, which is satisfied as well. So interestingly, this, in fact, is a valid vector space. And this example demonstrates why the joke about when people make that 1 plus 2 or 2 plus 3 or whatever, 1 plus 2 is 5 or 1 plus 2 is 4 is in fact now just proven to be true. Because if you look at, for instance, it should be obvious to anyone that you can define addition to be anything you like for a particular vector space. So the idea here in general vector spaces is to give us the flexibility to actually define addition and scalar multiplication, follow the 10 axioms, and according to that, we can prove if something is a vector space or not. Stop here. Thank you.